All right, we're now on our second video for our session number 2, and the topic is Chapter 4, Time Value of Money. So this is one of the most important things we have in finance, is to be able to quantify the different present values and future values. So we're going to start with just an introduction to what time value of money is, and then move on to show some generic approaches on how to use the Excel functions and formulas to solve these types of problems. Then we'll go through some scenarios, and they will be in 3 different types of patterns. One would be a single payment, the second would be a series of identical payments, and the third would be uneven cash flows. Finally, we'll wrap up with some other comments on other variations we often see in this field. All right, so let's start with something very simple. Let's say you have a choice of having $1,000 right now or wait 10 years for $1,000. What would you prefer? I think you all know the answer. The answer is we'll take the money now, right? So your instincts are correct, and that illustrates the time value of money. Now, the difference between an intuitive approach like you just had, like, oh yeah, I'll take the money now, compared to 10 years from now, is what is the quantified difference? Like, would you rather have $1,000 now or say $8,000 in 10 years? Now you're going to think about it a little more. So this kind of quantification is what we do in TVM. So let's try a second one, which I think is also easy for you. Let's try this one out. So if you put $100 now in a bank and it earns a 5% per year interest rate, what is it worth in 1 year? So that's a pretty simple one. You may not even need a calculator to do that math. You would say, okay, I put $100 in a bank. 5% of 100 is $5. So in 1 year, if I go back to the bank, I will have $105. And that would be the correct answer. So that is the second one. So does that make common sense? I think that does as well. Now let's push your brain a little harder. So let's say you go to the bank, but instead of just taking it out in 1 year, what happens if you take it out in 2 years? So why don't you think about that for a moment, and we'll go through it. And the question is it simply 5% times 100 times 2 years, so the total would be $110, or would it be something else? So take a moment. Okay, I hope most of you would think that, well, it's worth more than 110 because in that second year, I get to earn interest on my interest. In other words, I start year 1 with 100, and that grows by 5% to 105. But the second year, you start with 105, not 100. So 5% of 105 is $5.25. So you would actually end up at the end of year 2 with 110.25. And so that shows this notion that we call compounding. So I hope that common sense makes sense to you. And we'll go through now through some math. Okay, so congratulations. You've actually figured out, without knowing it, the formula for a future value. So let's just recap what you guys just did. First, we had this section here, and I will... All right, so first thing we noticed is that 1 year, this was the easy one, we knew it was 105. 105 is simply 100 times... The second year, we had this first term here, which represents 1 year's worth of interest, and then we multiplied that result times another factor to get to the compounding effect. So we ended up, as mentioned earlier, with 110.25. So here it is, just showing formulas and numbers. Now, if we generalize it, we can actually come up with a very important relationship, which is this formula, which works for any present value, any future value, any interest rate, and any period. So here it's present value, and in this case it was $100, times 1 plus the interest rate, which is 1.05, to the n power. Now this n power relates to this notion of compounding. So if we did this calculation using this formula, you'll see, of course, we end up with the identical number. That 100 times 1 plus 0.05 or 1.05 to the second power. So that formula validates kind of your notion of how bank interest would work, which again validates your notion that money today is worth more than money a few years from now. In this case specifically, you'd be indifferent taking $100 today or $110.25 if your sole objective were 5%. All right, so let's try the next one. Since we know this formula, we can then say and notice that in the algebraic equation, we could solve for PV. So if we simply solve for PV, we end up with identical terms but reordered somewhat, such that the present value is equal to the future value divided by 1 plus the interest rate to the n power. So it shouldn't be too scary because this formula is derived from the one we just figured out previously. So these are the two core formulas in time value of money. All right, so next I'm going to talk about the three types of cash flows that we normally confront. And depending on the cash flow, we use a different technique to solve the problem. So the first is what we've just been doing, and that's called a single payment. So that's just putting a certain dollar amount in now and waiting for what it's worth later. Or the flip side. If you got money 10 years from now and it's $1,000, what is the equivalent and what is it worth today? So this can go both ways. PV to solve the FV, FV to solve the PV. So that's a single payment. The second are series of payments. We call these annuities. And there are many examples of annuities. The thing that has to be the case is it has to be an identical payment. So you can't have payments that go up and down or maybe skip a year now and then. It has to be regular identical payments through the entire term of that particular time series or series of time, let's say. So examples, would you buy a house and you need to borrow money called a mortgage to repay the loan over 30 years. That's a perfect example of an annuity. It is a regular set of payments you make monthly until the end of the term, in which case you own the house. The third, type of pattern is uneven, where it's lumpy. It could be zero some years, positive some years, negative some years. And this is more example of like an investment. And the example that I would cite here is, let's say you buy an apartment house in San Francisco. So your initial cash flow right away is to pay a lot of money. And then each year as the owner of the building, you will get cash flow. Some years could be high, some low, some may be negative where you have to make improvements to the house and you're ending up putting in more money. And at some point out in the future, you sell the house or sell the apartment and you get a big, hopefully big lump sum of cash when you sell the house. And now you have this very uneven set of cash flows. And we use time value of money concepts to evaluate those cash flows and figure out, in this example, whether the apartment is a good deal or not to be purchased. So these are three patterns that we will see in cash flows. And depending on the pattern, we use different tools. So next I'm going to show a picture. It's often good in time value of money problems to visualize it, and sometimes it's pretty obvious and you may want to just take a shortcut and not do it. But I find that it's kind of worth sketching it out just to see what it looks like. So here's just a generalized picture of multiple cash flows where we are trying to figure out the present value. Here we have time being signified here as 0. So right here, we're at time 0. So time 0 in time value of money talk is today. So today is time 0. Next, we have cash flows that are for time 1, time 2, and time 3. So these three cash flows are at the end of those years. Then, as we did in class the other day, we have this thing where we sell an item at end of year 3 or the beginning of year 4. So those actually compress as if it were done on the very last day of year 3. So just in realistic terms, the last day of year 3 is very similar time-wise to the first day of year 4. So as a matter of convenience, we normally collapse those two into one bigger cash flow at the end of year 3. So the idea of a PV says if we take that cash flow, bring it back to today, take this cash flow, bring it back to today, and do it for each of the cash flows, and we end up now with the 4 different cash flows that now are all in today's dollars without any kind of blur because of time. And we end up with this very important notion of the net present value, which is the sum of all the cash flows in that particular pattern. And so if we had a price to buy this investment, let's say, the NPV is below, which means let's take the present value of all the money you get and subtract from that the cash flow to buy that particular investment. And if the NPV is a positive number, that means that the money you get is worth more than the money you pay, which is a good thing. If the NPV is a negative number, that means the money you get is less than the money you pay, and that would not be a good investment. So that's just a very simple example of how we use present value and how net present value is the most useful approach to doing a valuation of an asset. Next, we can go the other way. So in the previous example, we brought everything to today, time zero. But what if we want to know what something's worth in the future? In which case, we're pushing everything out forward instead of pulling them backward to today. So an example here would be, again, put down some money, and let's say we invest $100 today. And then a year from now, we invest $105. And year 3, we invest $110. And year 3, we invest $7,000. So in this case, we go the opposite direction. We take this cash flow of 0 and say, how much will it grow as of this point in time? Then we take this cash flow at the beginning of year 1 and we say, how much will that grow for that particular period? And so in this case, the future value equals the sum of what everything's going to be worth out at time 3. So that's a generalized picture of future cash flow, where money flows at a certain time and then you sit and wait, let it grow, and see it accumulate to some later point in time. So that's this notion of future value. So here's a general approach to using TVM problems, and then we'll jump right into Excel. So the first step is to determine the cash flows. It's very important to get both the dollar amount correct and also when the money moves. Since time is money, it matters whether you get it in today's terms or year 1, year 2, etc. So get the dollar correct and the timing. Second is to determine what's the interest rate. Sometimes in calculations we call it the discount rate, or in your bond calculations it was equivalent to the yield to maturity. The third is, I always like to draw a little picture so I could visualize what the money flow looks like. That's just for my approach to testing the reasonableness of the solution. And then the last step is to do the actual calculation. Now there are 4 ways to do it. One is this old-fashioned way where we use present value tables. We have them in the book, but I haven't used them in years, frankly. There's far more efficient ways to do it. Second is to use a regular calculator. A regular 4-function calculator could even do the trick for most calculations. I don't recommend that either because it's quite tedious. The third is to use a financial calculator. And for many years, we taught finance where we required students to buy a financial calculator. Now, if you want to learn a calculator, I welcome it. I happen to like calculators, but it's not something I'm going to push as our primary learning. Our primary tool these days is Excel. So if you want to learn how to use a financial calculator, go ahead and buy one. I would recommend a Hewlett-Packard 10 or 17, 10B2 or 17B2 Plus. Those are my favorite calculators. I can explain why if you're really geeky. And if you want to skip the financial calculator, it's fine. We're going to use Excel. So I'm going to focus our teaching on Excel, but I just wanted to point out that there are multiple ways to solve time value of money problems. So next we're going to get some scenarios using time value of money, but first I'm going to give you a little Excel lesson. This sheet is posted in my courses along with the videos, so if you want to pull this up, you're certainly welcome to do so. So you'll see the tabs along the bottom, and the tabs start with general TVM instructions, and that's what I'm going to do now. I'm going to go through kind of a generic approach to most of the things that we will be doing using TVM. And then each of these subsequent tabs are going to be examples of different cash flow scenarios and business scenarios, and then we'll use these tools and see if we can do those calculations. So first is that there are 2 basic ways to solve time value of money problems. The first is to use the formula that we just derived, that PV and FV formula, and simply code that into the cells in Excel. And I'll call that using formulas, right? Where we say PV equals FV divided by 1 plus I to the n power, right? That's a formula. The second is that Excel has some very powerful functions where you don't have to do quite as much work to do the mathematical equivalent of doing these tables. And depending on the scenario, we'll use one or the other approach. So as we use the tabs, I'll illustrate how to do those, and sometimes I'll actually show both. All right, so let's jump into some examples. So here we have our friend that PV equals future value divided by 1 plus interest rate to the n power. So let's say we had this particular cash flow example where we had 100, 105, and 71.10. And the interest rate is 10%, 0.1. We could just format that as a percent if we'd like, but it's 10%. So first, the factor, you can either put a plus or an equal sign to start a formula in Excel. So whatever's most convenient. So let's say plus. Plus 1 divided by open parens 1 plus, lock onto the discount rate or the interest rate, hit F4 so that that's an absolute reference, close parens, the little caret size raises it to the power, and then let's use this field to signify the number of years. We do that as a relative reference so that as we copy it, the formula is still correct. So that would be 0.9090, which means $1 a year from now is worth $0.90 to us today. If we copy that formula, Control C, Shift over and enter. So if we copy that formula, you could also drag and drop, of course, you would see that it goes to 82 and 75. And so money is worth more earlier than later. And in this particular case, $1 3 years from now is worth 75 cents today if the interest rate is 10%. So now we can get the present values, which again is equals or plus the factor times the cash flow, and copy that across. And we end up with these dollar amounts. And if we do the total equals sum, open parens, shade the 3 cells, close parens, we end up with $5,519. So $100 a year from now, $105 2 years from now, and $71.10 3 years from now is worth $5,519 today. So that's an example of using the formulas, the ones that we just derived. And here was a little picture of it, right? 100, 105, 110, 7,000, all future value. So let's do the future value using the formula that we're accustomed to and we just derived. And let's just clear this out and let's do our example. So same format as we saw above, and I'm trying to keep it consistent so we can focus on the differences. So at time, and we're going to start at time 0, 0, 1, 2. And at time 0, we put in $100. At time 1, we put in 105. At time 2, 110. And at time 3, we put in 7,000. Okay, so now what we're doing is we're pushing money out. We're investing it and not getting it until later. So the interest rate is 6%. Do something different. So now the factor is plus 1, open parens, 1 plus the interest rate. Let's lock it, F4, close parens, to the power of, in the first case, it's 3 years because it's out from year 0 to year 1, 2, and 3, right? So it's 3 years. The next is, and I'll just copy it over and then adjust it. So I'm going to copy it over here, but I'm going to have to edit it because the second one is out for 2 years. F2 is the edit key. So I'll do that again. You put your cursor on the cell, hit F2 to get edit. I'm backspacing and making it 2 years. Okay. The next one, same thing, F2, and this is going to be out for 1 year. And in this case, it's actually out 0 years because in year 3, on that day, we put in 7,000, we get 7,000. So now it's the same formula, is the factor times the cash flow, copy it across, and we end up with that. And the total cash flow equals the sum of the series, and that's 7,353 and 68 cents. So if we put in this cash flow stream of 100, 105, 110, 7,000, at the end end of year 3, we would have 7,353.68. All right, so that is using the future value formula in order to handle cash flows. Now, those are using formulas. Okay, the other approach is to use Excel functions. And these are specific little programs within a program that does the heavy lifting for us. So I'll show you by examples, probably easier than trying to explain how a function works, all right? So here we have a table, and let's just start right here, which says, what if we know the present value and we're trying to solve for the future value? And what if the information given are 12% interest rate for 5 years, there are no other intervening payments, it's just a single payment, the present value is 500, and the question mark is, what is it worth in 5 years? And there's another parameter that we often just leave as the default, and it is 0 if it's the end of each period that the cash moves, or 1 if it's the beginning. The vast majority of analysis in finance, the cash moves on the last day. So that's why we can either put the 0 or just accept the default and not have to do any more work. And I'll show you exactly how that works in a moment. So we could go through that formula approach that we just saw previously, or we use this handy formula, and it's right here. Equals FV, open parens, rate, then the periods, then the payment if any, then the PV, and then the type. So let's just do that. So equals FV, and what's cool about Excel is when you start the function in open parens, it gives you a prompt on the syntax. So you see right here the syntax. So the first factor is the rate, then you comma. The next is the number of periods, which is 5, comma. Next is the payment, which in this case is 0. There's no other payments. And then the present value of 500. And since it's at the end of the period, we're going to be okay with the default. So I just close parens, enter. So what this means is if I get $500 now, because 500 is a positive number, then I have to pay out $881 in 5 years. And that would yield to the cash flow stream exactly 12%. All right. So, oh, by the way, let's say you say, wait, I don't want to give out money. I want to get money at the end, right? Which means my present value, I'm going to invest 500. So it's negative 500. And watch what happens. It just flips signs. So this scenario is the PV is I put out or I invest $500. And in 5 years, I will get back $881. Notice that the signs flip, but it's just basically like the picture, which is the flowing in, which is the flowing out of cash. Next is we're going this scenario. What if we know the future value and we want to solve for what it's worth today? Very similar scenario, except notice that the unknown is now PV, the known is now FV. The formula for is very similar again, equals PV, open parens, and it'll prompt you for interest rate, comma, period, comma, payments, 0, comma, what is the future value? 500, accept the default, and enter. And that's 283. So what this means is $500 5 years from now at a 12% interest rate is worth 283 to us today. Again, we could do the opposite sign if that's easier to visualize. Let's say I want to know what would I invest today to get to that number. It would be I will pay back 500 and I would get $283. If I get a positive number, 283 today, and I wait 5 years to repay it, at the end of 5 years, I'll have to pay $500. That's the similar item to the PV example. All right, so now let's do an annuity, which is, again, a series of payments in identical dollar amounts for exactly the same interval, namely each year or each month. So let's just start with this part of the box. Notice that the format is exactly the same as above, and the function is even the same. So we'll go with future value. So equals FV, open parens, and what is the rate? 12%, comma. What is number of periods? 5, comma. What is the payment? And now we do have a payment. In this case, we're paying $50 per year, comma. What's the PV? There are none because we're just making annuity payments. So it's 0, and we can just close parens because we accept the default of payments at the end. So the answer is $317. So if we put in $50 a year for 5 years, which is $250, that accumulated interest over that period would end up with $317.64. So that is a future value. Same kind of thing we could do for present value. So this is the scenario. if we're getting money up front now and then we're paying money over the next few years. And this is like a car loan, right? Where you get money from the bank to buy your car and then you're paying back the bank every month. So let's do the formula. Equals PV, open parens, and you say the rate is 12%, comma, the number of periods is 5, comma, the payment is 50, comma, the future value is 0. There's no other payment. Close parens, enter. So the answer here is if you pay $50 a year for 5 years with a yield of 12%, that lender would give you $180 today. So that is using the function of PV and FV for, in this case, an annuity. All right, so next we'll do the very common scenario of uneven cash flows. And so it's very similar, as you'll see, to the formula approach that we used above. But now we're going to lay it out for uneven cash flows. All right, so here are the cash flows. Let's say we bought something for $50,000, and in each year we get cash flow from the investments. Let's call it an investment. And then at the end of year 5, we sell the investment for $100,000. So the total cash flows is represented by this row of information, all right? Starting with one negative, which is the investment, followed by positive, which is cash flow to us as the owner. So next thing we need to do is to determine the factor. And we've done this factor previously, so this should look familiar. Equals 1 divided by, open parens, 1 plus, the rate of interest, lock it as an absolute reference, close parens, raise it to the power of the number of years. And we'll copy that, Control C, Shift, over to the end. Now notice that the factor for T0 is 1, which is by definition. If you had $10,000 today, what is it worth? $10,000. So the factor for today is always 1.0. So now we get the present values. So we have $50,000 negative times the factor of 1, which is the easy one, and copy that across. And now we have this idea of a cash flow out of $50,000 in today's terms. Next year, in today's terms, $900 worth. So each of these cash flows are brought back to today. So everything goes back to what we call T0. And when we sum them up, equals sum, open parens, shade the whole stream, is a positive 39,572, which means we make money, right? It means that if we invest $50,000 and get this cash flow, the net present value of this investment is that we would be 39,000 to the good for this investment. So we like that, right? If it's a negative, that would mean that the investment up front is greater than all the cash flows that come subsequent to that. And that's what would happen if the sign flipped to be a negative, which means don't do it. All right, the last example is where we use the net present value function. So rather than use formulas, we're going to use the function. So this is a shortcut. I think you're going to like this one. So it's the same pattern, right? Same cash flows as we saw earlier, right above, right there. And it's the same interest rate, 8%. And we know that this number was the result of our calculation. Now, we can do this with one calculation. Equals NPV, open parens, the rate, which is 8%, comma, and then this is the trap for Excel, is start with year 1. Do not put in year 0. So it's only for the future cash flows. Close parens, and that will get the present value of years 1, 2, 3, 4, 5. And then we have to then reflect the initial investment separately as 50. And when you hit enter, we end up with exactly the same number. Okay? And so we see that this NPV formula, this one, which is actually NPV formula and reflecting initial cash flow, is a shortcut to doing this fairly long calculation using the formulas. All right. So what we've done just now is looked at many of the tools, the kind of the underlying tools to solve time value of money problems. So I'm going to go back to the PowerPoint, and then we will then do some examples one by one and give you guys a view of how this thing works. All right. So here are some scenarios. You say $5,000 today, how much would it be worth in 5 years? Second, you want $1,000 in 5 years, how much do you have to set aside today in one payment to get to that $1,000? Third, if you save $1,000 per month for 5 years, how much would you have saved after 5 years? Fourth, you just won the lotto. Would you rather have $1.5 billion over 29 years, and that just means every year you take $1.5 billion divided by 29, or would you rather have $930 million today, right? Next, there's an apartment building for sale now for $5 million, and would it be wise to buy it, operate it for 3 years, then sell it for a profit? And we'll be looking at cash flows in that scenario. And sixth, if you borrow $1 million now to buy a 2-bedroom condo in San Francisco, what would you pay per month on your mortgage payments? So notice that each of these are fairly common business scenarios, and they all relate to money and time. So the first thing we should look at is what is going on here. And so in our new language, we see that the first scenario is a future value of a single payment. So we have a dollar amount today, and we're going out to 5 years. Second is it's the present value of a single payment. So the single payment is $1,000, but that's in 5 years. You want to bring it back to today. What is it worth today? Namely, present value. Third is a future value of an annuity. So that means we save and kind of put away $1,000 per month for 5 years. What is the future value that's accumulated after the 5 years? The fourth is a question of the present value of an annuity. Annuity is over 29 years, we'll get regular payments, and we're going to compare that to a lump sum payment now and say which one is more financially valuable to us. Fifth, this is a classic example of a net present value of an uneven cash flow. That's an investment. And last, we're computing the payment that would be due upon an annuity, in this case, a mortgage payment. So although these are kind of familiar sounding scenarios, or you can at least envision them to be typical financial or business scenarios, what we need to do is discern which of the tools that we just looked at can we use to attack those scenarios. So we're going to do each one of these in turn. All right. First is, you have $5,000 today. How much is it worth in 5 years? Rate of interest. Actually, I think we changed it to 6%. And so the formula is the future value equals PV times 1 plus the interest rate raised a number of years. So the recommendation is to draw a little picture. So if I draw a picture, 5,000 today, and I save, so that's a negative, it would look like this, some negative number. And then in 5 years, it's going to be some big number, right? Hopefully much larger. So these are the two cash flows, and that's going to be our calculation. So now let's hop into Excel. Okay, so let's do the first scenario, which is you save $5,000 today times 0, and you want to let it sit there for 5 years. So let's just put that in the grid. So cash flow today is negative 5,000. And there are no other subsequent cash flows, so I'll just, and the interest rate is 6%, 0.06, and the factor is plus, open parentheses, 1 plus that factor, lock it, raise it to the power of how many years are outstanding, are remaining, how far will be out, 5 years, okay? So the PV is that times that. And that, in this case, is the answer since there are no other cash flows. So the entire answer is captured right there. That $5,000 invested today would be worth $6,691 in 5 years at a rate of interest of 6%. Okay. The other is to use, again, I copied this forward, use the scenario of the function. And here we know the present value, and what's unknown is the future value. So it's this one. I know the PV, and I want to solve for the future value. So here, what is the rate of interest? Is 0.06. What is the number of periods? The number is 5. What are the payments? There are no subsequent payments. What's the PV? Negative 5,000. What is the future value? That's the question mark, right? So that's what we're going to solve. So let's solve it. So the future value is equal FV, open parens, and look at the parameters. Rate is that, comma, number of periods is that, 5, comma, what are the payments? No payments, because there's just 1 up front, comma. What is the present value? Negative 5,000. Close the parens because we accept the default. And the answer is 669113, which is exactly the same as that. So either the formula approach or the PV or FV formula works well in this case. All right, so that's the first example. What is it worth in 5 years? It's worth $6,691, and we can arrive at it using a formula, which is frankly very simple in this case, or we could use a function, Excel function of future value. All right, so that's the first example. Pretty straightforward. In the example, I'm going to show how to use it if you had a calculator. I'm not going to show you this now in the lecture, but I'll put it in a slide deck so you can see it if you happen to own or want to own a financial calculator. All right, second is PV is a single payment. Now the scenario is you want $1,000 in 5 years, and we want to set aside one payment today to get to that dollar amount in 5 years. Interest rate is 6%. The formula is here. We've derived that one before. The PV equals future value divided by 1 plus interest rate raised to the n power. If we were to sketch the cash flows, $1,000 in 5 years. So you want to get that. So you want that's a positive number. We want $1,000 bucks, all right? And the question is, how much do you set aside in one payment right now at time 0? So some negative number. So what negative number now do we set aside so that it grows to be $1,000 in that amount of time? So that is the scenario. And so let's look at the numbers. Again, we have two choices. We use the formula or a function. And so we want to set aside, if you want $5,000 here, and that's 1,000. And the interest rate is 0.06. And then the factor is plus 1 divided by, open parens, 1 plus the interest rate, lock it, raised to the 5th power. And that's the factor. So every dollar is worth 74 cents today. So if we want $1,000, then we just multiply $1,000 times what it is worth today. And the answer is 747. It will grow over 5 years at a rate of 6% to hit our target number of $1,000. Right? So that's using the function or this formula. Next, we use the function. And here we'll use the PV function. So the rate of interest, 0.06. The number of periods, 5. The number of payments, the payment amount is 0 because there's a single payment. The PV is our question mark. So that's going to be our Excel function. And the FV is $1,000. Okay, so let's try this out. Equals PV, open parens. What is the rate? Comma. What is the period? 5, comma. What are the payments? 0, comma. And what is the FV? $1,000, close parens, and you get the same number. So 747 through a formula is identical to 747, which is the Excel function. So either approach works. It's just a matter of your choice, and they're both, I think, reasonably easy. All right? So that is scenario number 2, where we're solving for the PV of a single payment. Third scenario, if you save $1,000 per month for 5 years, what would you have saved up? The annual interest rate is, again, 6%, and we sketch cash flows. Now, this one's tricky because what we've got now is a lot of cash flows. It's $1,000 per month. So what that means is we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? We'll have 12 payments in year 1, and likewise, we'll have 12 payments in year 2. So you can visualize that we would have, over the course of the time, we would have 60 payments. That's a lot of cash flow. So the question is, if you put in that amount of money, what is it worth at the end, right? So let's show you how to do this, and there's going to be a lesson in this one. So this is the next tab over. It's 1,000 per month, 1,000, but we have it for 60 months. So copy that, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way out there to 60 months, right? And then we'd have to have a factor, 0.05 divided by 12. So that'd be the factor, and we'd have to copy this out way out there, somewhere out to 60 months. And we could do this and multiply the PV factor times the cash flow out for 60 months, but that would be quite tedious. So here's where there's a clear preference. Do not do 60 months and 60 columns. Let's just jump right to using the function. And we're trying to determine the future value. So that is, we know the payments, and we're going to go out to the future value. So we use this one, and actually I'll just write know the payments, want the FV. Okay, what's the rate? Again, it's monthly, so equals or plus 0.06 divided by 12. And then what's the number of periods? 60, right? 60 months is 5 years. The payments, $1,000 a month. And let's have us put out the money. We're going to save $1,000, so we're going to take out of our pocket $1,000. And the present value, nothing. I mean, that's 0 at this point. And the question mark is here. Equals FV, open parens. Again, this is going to get boring. The rate, but remember it's a monthly rate. So it's the annual rate divided by 12. The number of periods, 60 months, not years, comma. Then what is the payment amount? $1,000 negative. We're paying out. What is the PV? There's no additional PV. And then what is the future value, or type rather? We'll take the default, close parens, enter. And we'll end up with the number of 69,770. So if we put $1,000 a month in the bank for 5 years, over that time period, it would accumulate to 69,770. All right, so that's the answer to scenario 3, 69,000. And notice that we could have done this all the way out to payment 60 or month 60, but that's quite a bit more work than simply doing this calculation right there. Okay. All right, so next scenario is PV and annuity. So would you rather have $1.5 billion over 29 years, which is the equivalent of 51.7 million, or I guess it's a different number, or $750 million today? So we actually have a choice. So that's why there are two sketches here, two graphs. So let's grab a pen, and let's say, would you rather have 51 million a year for 29 years? So the first scenario is you get all these payments. So we get 29 years of 51.7 million per year. Or would you rather have a massively large lump sum here now? Okay, so that's the choice. All right, so that's pretty ugly, I must say. So when we move to the tabs, we're going to use, again, since it's so many years, I'm not going to bother with laying out 29 years of columns. So I'm going to go right to the case of a PV. So here, I'll just write here, we know the payments, and we want the PV. Okay, so the rate is 6%, 0.06. The number of periods, 29. The payments, now we do have payments, 51.7. And the PV, that is our question mark. And so this is the one that should be yellow. And then the future value, there's no other payments because we're happy to just get 29 years worth of 51 million a year. So now let's solve for it. So equals PV, open parens, what is the rate? 6%, comma. What is the period? 29 years, comma. What is the payment? $51 million, comma. Is there any subsequent payment? No. Close parens, enter. Oops. And the answer here is $702 million. Now you recall that the question was, would you rather have 750, right, versus 702? So this is really the choice. And if these are our choices, I'd rather take the 750 now. Right? So here we have, what's the present value of the cash flow to us? 702 What are they offering me? $750. I'll take the $750. We should all be so lucky to get one big check for $750 million today. Okay, so that's scenario 4. Scenario 5 is kind of a typical investment scenario of an uneven cash flow. And here we had other info. As we mentioned, we needed that info. It looks like this. The building is for sale for $5 million. The first thing is a big negative. That's negative $5 million. And then we operated for 3 years. So we get small cash flows, a little bit here, a little bit more next year, and a little bit more the following year. And then we sell it at the end of year 3 for a very big number, right? So we get, I just put it inside, I get a very big number, right? So the question mark is this make money? So let's try this out. Okay, here it is in Excel, and let's put in the cash flows. So let's start with the initial investment. It's a negative amount because I'm paying money out. So it's out of my pocket, it's a negative. Negative 5, and we'll do it in thousands. So it's negative 5,000. And then year 1, we're given that we get 100, positive. Year 2, 105. Year 3, 110. And at the end of year 3, we sell it for $7 million. So we had cash flows that are investment, and then the 3 annual cash flows. And then we get a big check at the end of year 3. And so here's our sum, and we should be pretty good at our factors these days. So the discount rate here is 10%, right? So 0.1. And so what are the factors? Plus 1 divided by, open parentheses, 1 plus the rate of interest, lock it F4, close parentheses, raise the caret to the power of the years, and copy that to the years. Again, it's 1 because at time 0, money's worth what it's worth. So the cash flows equals the factor times the cash flow, and copy that. And so those are the cash flows. And when we do the sum, equals sum, we end with a positive 520. So again, since it's an investment, the cash flows, which are the positives, are larger than the negative, which is investment. So this is a good investment, right? So we would take it. Now, you'll notice that we could have done this using the Excel function. So that's the NPV function. So let's use that approach. Equals open NPV, open parentheses, and it gives us parameters. What's the rate? The rate is 10%, comma. What is the series? Again, the trick is never start with T0, only go with T1 and beyond, close parentheses, and then reflect that you had to spend money to get that cash flow, in this case 5,000, and we end up with, better be the same number, 520. So that's still good, right? And so these results equal these results. And again, notice that we could use this formulation here, or we could just use one very powerful Excel function in order to figure out the answer. And we end up with exactly the same results. So the final one is a payment on an annuity, and this is the mortgage. We borrow $1 million, we buy a 2-bedroom condo, and what's our monthly mortgage payment? With the rate of 4% per year, annual, 30 years with monthly payments. And so if we sketch this cash flow, we'll end up with lots and lots of payments. We would get a very large amount of money up front. That's the funding from the bank. And then every month we pay a little amount of money, all the way out 360 times, right? And that 360 leads back to the amount of mortgage. And that's how we do it. Okay, so let's jump into Excel. All right, so let's go to Excel and see how to do that calculation. Here's the information. And again, if we're doing a 30-year mortgage times 12, that's 360 columns, and that's quite painful. So let's use the function. And the function is a little bit different. We haven't used this one yet. It's a payment function. Here we know the PV, which is the $1 million. We know the rate, which is 0.04. But that's a monthly rate, so it's 0.04 divided by 12. And then the number of periods is plus 30 years times 12, 360 months. The payments, this is the unknown. So that's the question mark. And the present value we know is $1 million. And then the future value is 0. We're going to fully pay off the mortgage. So that actually, let me just make it clear, that's not an unknown. And so let's use the function. So it's equal PMT, open parens, and again, it'll coach us through. The monthly rate is that, which is 4% divided by 12. The number of periods is 360, comma. The present value is $1 million, comma. The future value is 0 because there are no subsequent payments, and accept the default. The answer is 4,774. So what this means is in order to get a mortgage of $1 million at a rate of interest of 4% over 30 years, the monthly payment will be 4,774 per month. And that's how we calculate that. So that one is obviously a very, very commonly used time value of money formula. All right, a couple of other comments, then we'll wrap it up. What if the time period isn't once per year? There's a variation or a refinement of the FV formula, future value formula, and it goes like this. It equals PV times 1 plus the interest rate, but in this case, it's the nominal interest rate divided by the number of times a year, right? So in the past, we use 1 payment per year, so it's simply the rate of interest divided by 1, so that's obviously the same rate of interest. But if it were monthly, it would be the rate of interest divided by 12, quarterly, the rate of interest per year divided by 4, etc., etc. Okay? And the power, when we're doing the compounding, would be the number of times per year, that's M, times the number of years, which is N. So that's the formula. So let's look at just a couple of examples and how it works. So if we had $100 at 12% nominal for 5 years, semi-annual, PV is 100, right there. The nominal is 12, that's the numerator. The M, which is the frequency, is 2 times a year. Since it's semi-annual, that's 2 times per year. And then the power would be number of years, 5 times 2, which is twice a year payments. And so the future value would be $179. Okay, now let's look at a chart that compares the different compoundings. If you compound it once a year, you'd have 176. If you compound it semi-annually, 179. And what you see is the more compounding frequency, or the higher the frequency, the higher the dollar amount. To the extreme here, where we compound daily, where it would be $182. You guys just heard Charlie. All right? Wrapping up this chapter, what we saw first was an introduction to time value of money, which hopefully you agree is common sense, that money is worth more money now than later. We then went through a full set of instructions on how to use Excel using either formulas or functions. Then we applied it to 3 kinds of scenarios of single payments, annuities, and uneven cash flows. And then we just did one variation on a theme. Of course, there are many, many other variations, but one of the more common one is the compounding period, whether it's annual, quarterly, semi-annual, or even daily. So thanks, and I will see you in class this week. Bye-bye.